Hello everyone, welcome to NS Academy. So today we're going to look at this integral 0 to 1 ln of 1 minus x upon x dx. Now this is in traditional sense not a very clear integral to approach to, not any fundamental methods are going to work on this one. We can call this integral I. So that is why I'm going to show this integral and how to approach integrals of the same time. So in order to do this integral, you might think of a few tricks that you have learned while doing this kind of integrations or where logarithm is associated to it, like let's say putting x equals to sine square theta or cos square theta and stuff like that. But in this case, what we need to do is we need to understand the expansion of log of 1 minus x around the point 0. And this turns out that this basically is minus x squared upon 2 minus x cubed upon 3 and so on it goes. In summation notation, we can write this as minus summation n equals to 1 to infinity x to the power n upon n. And this only works if x is between minus 1 to 1 strictly. So it cannot be equal at the endpoints, obviously. Otherwise, you do know that log of 0 goes up to negative infinity. So these are the limits that we need in order for the expansion to work. And it is the range in which this logarithm of 1 minus x converges. So in order to do our integration, we are going to use this expansion. So we can rather write here integral of 0 to 1. And in place of ln of 1 minus x, we can simply put in this summation expression instead of ln of 1 minus x, which is summation minus n equals to 1 to infinity x to the power n divided by n. And then there is a 1 by x there, dx. And on simplifying a bit, you get that this is simply 0 to 1 minus summation n equals to 1 to infinity x to the power n minus 1 by n dx. Now, up to this point, it should be clear. And how we arrived at this expansion is something we can talk about in other videos. This is called the Maclaurin expansion. It's called the Maclaurin's expansion. And this is a very general, specialized form of Taylor's expansion. You might have heard of Taylor's expansion if you're doing your basic calculus right now. Not basic in the sense, but the expansion which is required in most. So I can just show it here a little bit. For any function f of x that is differentiable up to some order, you can do a partial sum. And if it's differentiable continuously, you can simply write an expression like this: f of x equals to f of 0 around the point 0, of course. Then f dash 0 multiplied by x, then f double dash 0 upon 2 factorial into x square, and so on, assuming that f is differentiable at the point 0 continuously, that is, for all derivatives are defined. So this is called the Taylor expansion. So more about that later in some other video. So what we can do here is now, in this expression, we can interchange the summation and the integral basically. And that is allowed because this whole thing, it's a completely positive quantity since x is between 0 to 1. If you ignore this negative sign outside, this just basically comes out. And also the sum converges because in the range 0 to 1, we have seen that logarithm converges, right? So using the dominated convergence theorem, or you can simply put it like this, that if you have something which converges absolutely here, you can simply put this value. So this is not an alternating sum, right? And this thing converges and all the terms are positive if you do not take care of this negative sign because it basically comes out. You can write this expression n equals to 1 to infinity 1 by n into x to the power n minus 1 dx. So x is the integration variable here. So the whole summation can just basically come out like this: n equals to 1 to infinity 1 by n, and then you have 0 to 1 x to the power n minus 1 dx. Now this is a fairly simple integration. You know that this is equals to 1 by n, and thus the integral basically turns into negative of n equals to 1 to infinity 1 upon n squared. And this simply is 1 by 1 square plus 1 by 2 square and all the way up to infinity. This is the particular case of the Riemann zeta function. And you can write this basically like this: zeta of 2, which is a given value of pi square upon 6. So basically, The sum of the square of the natural numbers reciprocals when added up to infinity gives you a pi square by 6, which is like very weird, but we do have lots of proofs on this one, and I also intend to show some of them. Not in this video though, but the Riemann zeta function basically is defined like this. The infinite sum of from n equals to 1 to infinity, 1 upon n to the power s. And notice that the power s can also be a real complex number. It does not only need to be a real number. And this is defined, this thing converges when real part of s greater than 1. So this is how the Riemann zeta function can be defined in terms of real numbers at least. And the answer to this integral is minus of pi square upon 6. So I really hope that you like this video. But the explanations for the Taylor expansions and of course the Riemann zeta function and special values like zeta of 2, zeta of 3 is irrational, then zeta of 1 diverges, zeta of 1 is basically a harmonic series, stuff like that. I wish to put a lot of this on this channel. Thank you for watching.